this video we're going to be going through the roots of unity. So what does this mean? The roots of unity are basically just the roots of 1. Now if we've got z cubed equals 1 where z is a number in the complex plane, now you'd think that the only answer is 1, but using complex analysis we can actually get a lot more roots than just 1. So the way we do this is by using the Euler form. So we're going to say that z cubed is equal to r cubed e to the 3I theta. Now this is basically just using the fact that z has a modulus of r and an angle of theta, and we can write it in this form like this. Now all we need to do is write this as in that form, and then we can evaluate what our roots are going to be. Now before we do that, there's one more step we need to add into this angle here, which is plus 2n pi, and this is multiplied by I. So basically what we're saying is that z cubed equals r cubed e to the I times all of 3 theta plus 2n pi. Now why is this 2n pi significant? Well, we know that each of the sine, cos and tan functions repeat every 360 degrees or 2 pi radians. So this n pi, or this 2n pi, is going to give us extra roots. Now you might think that it's just going to give you the same answer, but when you divide through by 3 by cube rooting both sides, this will actually allow us to evaluate all of the roots within a range of 0 to 360 degrees. So what is the argument of 1? Well, that's just 0, so that's pretty simple. So we don't actually have to include it in this form. So we can say that z is equal to the cube root of 1 is just 1, because that's the modulus of z cubed. So 1e. And now we don't need to include this bit here, so we just need the 2I n pi. So I'm going to write, I'll factor out the I to make it a bit more simple. So I times 2n pi, and then we divide it by 3 because we're cube rooting. Now what this is telling us is that there's going to be 3 roots because it's a cubic equation and we've divided the 2n pi by 3, so we should expect to get 3 values. Now when you have a number such as 3, you want to take the same amount of roots around 0 and 1 when you use n. So basically my n values are going to be anywhere between minus and plus. So because there's 3, we'll do 3 values around 0. So n equals minus 1, 0 and 1. So this is going to get me all my roots, and you'll see why it doesn't matter if we do it up to 2 or minus 2 in a second. So that means that z is equal to, let's start with n equals 0. So e to the power of 0 is just 1, so z equals 1. That's the root we expected. So this is for n equals 0. And now for n equals 1, we'll have z is equal to e to the 2I pi over 3. And for n equals minus 1, z equals e to the minus 2I pi over 3. Okay? Now, let's plot these on an Argand diagram. So z equals 1 is going to be over here. Z equals e to the 2I pi over 3. It's going to be roughly over here like this. And then z equals e to the minus 2I pi over 3. That's going to be measured anti-clockwise. Clockwise. And that's going to be somewhere over here. Now, let's say that we wanted to consider n equals minus 2. Or let's start with n equals 2. So for n equals 2, z is equal to e to the 4I pi over 3. So basically, this is just going to be 240 degrees. Now, if we measure this angle here, this is 2 pi over 3. And then if we measure this angle here, this is also equal to 2 pi over 3 because it's going backwards minus, so it's going to be 2 pi over 3. Now, for all of them to add up to 360, or 2 pi, this here also has to be 2 pi over 3. Now, what that means is that this argument over here is just going to be 2 pi over 3 plus 2 pi over 3, which is 4 pi over 3, but that's the same as the root that we had from doing the minus. So you can see that n equals 2 is just the same as n equals minus 1, which is why you don't need to go up to 2. So in this case, our power was 3, so we only needed 3 values around 0, minus 1, 1, and 0. And that gives you all 3 roots. So these are our roots. Z equals e to the 2I pi over 3, z equals e to the minus 2I pi over 3, and z equals 1. Now let's do this for a more complicated example with a power of 5. So here we've got our equation, z to the 5 equals 1. So again, we're going to write it in Euler form, and then we're going to add the 2n pi at the end. So z to the 5 equals 1 to the 5 times e to the I times 5 theta, but theta is equal to 0 in this case, plus 2n pi. Okay, now we cube fifth root both sides rather. So z is equal to 1 e to the I times 2n pi over 5. Now, since we have 5, we're going to have to take 5 values around 0. So we're going to choose n equals -2, -1, 0, 1, and 2. So let's start from -2. So n equals -2. This gives us z is equal to e to the -4 I pi over 5. N equals -1 gives us z is equal to e to the -2 I pi over 5. N equals 0 gives us z is equal to 1. Again, we expect this because the fifth root of 5 is, the fifth root of 1 is just 1. For n equals 1, this gives us z is equal to e to the 2i pi over 5. And for n equals 2, z is equal to e to the 4i pi over 5. So, once again, let's plot an Argand diagram and see what this looks like. So for z equals 1, again, it's going to be over here. Z equals 2i pi over 5, so plotting this one. So pi over 5 is going to be 72 degrees. 36 degrees. So 2 pi over 5 is going to be 72 degrees. So somewhere over here like this. And then 4 pi over 5 is going to be 144 degrees. So somewhere over here. And then you'll notice that these are actually complex conjugates. So this is conjugate with that, that's complex conjugate with that. So they're actually going to have the same real part, but just a negative imaginary part. So we can just plot this here like this. This is going to be this root, and then this one is going to be over here, like this. Now what you'll notice is this actually forms a pentagon. Now I haven't drawn it perfectly, but this will actually give a regular pentagon, and you can kind of expect that because it's the fifth root, so you can expect all of them to sort of make a natural shape like that. So these are our 5 roots. Z equals e to the 4i pi over 5, 2i pi over 5, z equals 1, and then these two above with the negative angles.